Okay, let's get right into it. When you think about getting a shot, it seems pretty straightforward, right? A needle goes in, does its job, and comes out. But what if I told you that getting that needle to the perfect spot, down to the millimeter, is actually one of the sneakiest, toughest challenges in all of modern medicine?
Take a procedure like prostate brachytherapy. It's a type of cancer treatment where these tiny radioactive seeds are put right inside a tumor with a needle. For that to work, you need incredible precision. But here's the catch. As soon as a needle goes into soft tissue, it doesn't just travel in a perfectly straight line like you'd think.
And that really brings us to the big question, doesn't it? Once that needle tip is inside the body, totally invisible to the naked eye, how in the world do you guide it exactly where it needs to go?
To figure that out, we first have to get down to the nitty-gritty physics of it all. We've got to look at this micro problem. Why do needles even bend in the first place?
Well, the phenomenon has a name. It's called needle deflection. It's just the natural tendency of a thin, flexible needle to curve as it moves through tissue. And the reason for it, well, it's probably not what you're thinking. It's all because of the very tip of the needle.
See, here's the thing. To cut through tissue, needles need a super sharp, beveled tip, that little angled point. But that angled design, the very thing that makes it sharp, creates an uneven force as it pushes forward. And that forces the needle to bend, to curve away from that perfect straight line you were aiming for. So your planned trajectory and the actual one, they end up being two totally different things.
And just how big of a difference are we talking about here? In that prostate cancer therapy we mentioned, the error can be up to 5 millimeters. Now, 5 millimeters might sound tiny, right? But when you're dealing with a really small organ and radioactive material, 5 millimeters is a huge deal. It can literally be the difference between hitting the cancer and damaging perfectly healthy tissue.
So, facing this really tough challenge, a team of researchers came up with a pretty ingenious solution. They thought, okay, if you can't see the band, maybe you can feel it. They came up with something they call a virtual sensor. Now, they didn't put some tiny little tracker on the needle tip. That'd be way too complicated and invasive. No, instead, they figured out how to calculate the needle's hidden position just by using data from the outside. Okay, so here's how it works. First, they mount this super sensitive sensor at the base of the needle, outside the patient's body. As the needle starts to bend inside, it creates these tiny forces that travel right back up the needle shaft. Then, and this is the cool part, a really sophisticated computer model takes those readings and calculates in real time exactly where the tip is. And finally, once the bend hits a certain point, the system automatically rotates the needle 180 degrees. This flips the angled tip, making the needle curve back the other way, basically steering itself back on course. And this isn't just some idea on a whiteboard. Nope. This is the actual robotic rig they built to test the whole system. They used this transparent gel that acts like human tissue, so they could actually see the needle's path and check if their virtual sensor was getting it right. And the results? They were pretty amazing. This chart here shows the final error. Without any correction, the error was pretty high. If they waited until the needle was 5 millimeters off course to make the turn, the error got smaller. But look at this, when they corrected it super early, at just 1 millimeter of bending, they were able to get the final error down to almost zero. They basically made a self-correcting needle. Incredible. So that's a fantastic solution for the tool. But there's a whole other, much bigger piece of this puzzle, the person who's actually holding the tool. And this brings us to the macro problem, the skill of the user. So we've seen how technology can solve the physics of a needle that bends. But what about the person doing the injection? What about their training, their experience, their steady hand? That is a whole different ballgame. The reality is there's a huge training gap out there. The qualifications for who can give injections vary wildly depending on where you are. There's just no universal standard for training. And this doesn't just apply to complicated cancer treatments. We're talking about all kinds of cosmetic and medical procedures. It kind of creates a lottery of care, where how good your treatment is can totally depend on who happens to be holding the syringe that day. So that brings us to a second and equally brilliant solution. This one isn't about fixing the needle while it's in motion. It's about perfecting the user's technique before they ever see a patient. And it all starts with a simple, really powerful idea.
What if you could give trainees a way to see the invisible, a way to get instant visual feedback on the depth, the angle, the path of every single practice injection they do?
So, how does this thing work?
Well, imagine a training dummy. The trainee uses a special syringe that has a tiny fiber optic cable in the needle, so the tip actually glows with light. They inject this into the dummy, which is made of different layers, simulating skin, fat, muscle, and each layer changes the light in a specific way. An internal camera watches how the color and brightness of the light change as the needle goes through each layer. And then, software analyzes all of that and gives the trainee an immediate score on how accurate they were.
It's basically a flight simulator, but for injections. Or you could think of it like a video game for medical students and doctors. The feedback isn't days or weeks later, it's right then and there. You know instantly if you were too deep, too shallow, or at the wrong angle. It lets you build that muscle memory and perfect your technique in a totally safe environment.
So after all that, where does this leave us? We've looked at two very different technologies, but they're both tackling the exact same problem of injection accuracy, just from completely different angles. Let's just break it down side by side. You've got the virtual sensor, which uses force and torque to correct the needle in real time during the procedure. The goal there is to make the tool smarter. Then you have the training system, which uses light and a camera to improve the skill of the practitioner before they even touch a patient. The goal there is to make the user better. And that's really the beautiful thing here. You have two paths to the same goal. One way is to create the perfect tool, a tool that can fix its own mistakes as it goes. The other way is to create the perfect user, someone who's so well trained that mistakes are much less likely to happen in the first place. And really, you need both.
Which kind of leaves us with one last thought to chew on. Both of these technologies are about making something invisible visible, one with math, the other with light. And it just makes you wonder, what other hidden challenges in medicine are just waiting for the right technology to help us finally see them?